Okay. Thank you, everyone. Thank you, Ruilong. I'm super excited to introduce Ruilong Li, who is graduating from my group. Um, I Ruilong was one of the first group of people that I accepted into my group, and but I was lucky because I was able to intern with Ruilong. Um, when I was at Google, Ruilong was my intern, not the other way around. And I got to know him. And it was really clear the moment you start working with him, you just notice how awesome Ruilong is. Ruilong is really awesome. And Ruilong is super amazing, technical too. I mean, he can do math. Did you know he was a math major? And he's an amazing coder. And he really, you can have lots of discussion and really an awesome person. And so I'm really happy that you were in my group and built all of these cool things. So yeah, thank you.
Thank you. All right. Thank you, Angju. Thank you for the kind words. And I'm really excited to spend my past 4 years here at UC Berkeley and meeting all the talented people here. And I guess today my PhD journey is about to coming to an end, and I'll present my projects, the projects I did during my past 4 years. And all of them kind of falls into this topic of efficient. Oh, yeah, sure. Uh, okay. I can't really hard find it. Okay, maybe we'll leave it there. Okay, so today's presentation is going to be about the collection of projects falls into this bucket of efficient 3D perception from imagery. So I'll start with the introduction about what is 3D perception. And okay, I really want to get rid of this. Okay, yeah.
It's unshared.
Yeah.
Okay, now you can put it. Okay, good.
Nice.
All right.
So yeah, I asked a question to the ChatGPT, what is 3D perception? And this is the answer it gives me. And I feel pretty happy about the answer, so I want to share. It says it's the ability that either by humans, animals, or machines to interpret the 3D dimensional structure of the world from sensor input. And the moment I saw this sentence, I feel like it exactly summarizes what I've been doing during my past 4 years at Berkeley. And by the way, this figure also corresponds to ChatGPT. So 3D perception is actually everywhere in the daily life, starting from Apple ID that everybody uses right now, and to those AR, VR immersive experience, like this IKEA app. And also, when we have the 3D perception algorithm, we could use it to reconstruct the real life world into the digital assets so that we could have this virtual tour experience in those real assets. And we could also use those assets for gaming and filming or VR, AR industry. And what's the coolest part about 3D perception is actually the following, that it is crucial for the next generation AI agents, including autonomous driving cars that Tesla haven't achieved L5, which is largely because the 3D perception system is not perfect yet. And for the robots in the future, that we don't really want, we not only want them to be able to chat with us, to be able to give us some pretty figures, we also want them to have the ability to perform a real physical task in the real life. So 3D perception, which allows them to understand the environments around it, is a crucial step for that. And the solution for 3D perception Actually, it's like this. Before I joined UC Berkeley, this is a project I have been doing before here, where I was a PhD, kind of a short 2-year PhD at USC. And we build a real-time system that take in molecular image and predict the 3D structure and texture of it. So you can see the quality is not yet there in this project, but it was pretty surprising when I first saw the results like this back then. And we demonstrated on the SIGGRAPH real-time live and surprisingly got a Best Show award. So I would consider it was pretty good back then. So under the hood, it was using a feed-forward prediction model that is trained with 3D supervision signals. But the 3D data back then was very limited, so the quality was not really there. And things changed after this NERF paper came out in 2020. It introduced a new paradigm for 3D perception, which turns this learning-based framework into optimization-based framework. It takes in the multiple captured images and using the differentiable volume rendering to reconstruct the 3D under the hood. The best thing about NERF is because this differentiable volume rendering builds the bridge between 2D and 3D, it allows us to get rid of the 3D supervision that we usually rely on in the previous large learning system. We could use the image instead to provide the supervised signal to the system. And since then, there has been an explosion on the NERF literature, either using NERF to perform some task like generation or 3D understanding or reconstruction, or simply just trying to improve NERF. And all of them is because like NERF is very easy to use and it provides super high quality visual results. So, but NERF was not perfect as the first paper. It was pretty slow initially. It took like 30 seconds to render a single frame. And since the NERF paper came out in 2020, it has been a lot of amazing works trying to improve the efficiency of NERF, either for training or for rendering or for storage. And among all of the works, there is a kind of special one that's lifting this quality and the speed to another level, which is the Gaussian splatting came out at late 2023. And after the Gaussian came out at 2023, there apparently seems to be another round of explosion on the topic of 3D Gaussian, either also using it or improving it. But recently, most recently, like since late 2024, there has been some works coming back to this trend of using learning-based approach because we have much better GPU now than 4 years ago. We have much larger data sets now. We have like transformer architecture with flash attention, much better architecture. So by leveraging all of those, the learning-based approach right now starts to shine again. And we see all those companies in industry are training extremely large models to do the task of novel alternatives here. But many of them requires extensive resource to train a model. For example, 15,800 hours for the first one in Adobe, and 40,800 hours for the stable virtual camera, which is Hans project from Stability. So in summarize, we now have like two paradigms of solving the 3D perception system. One is optimization-based solutions like NERF or Gaussians, which works great when we have enough observations and we don't need extra data to train a super large model to begin with. But the downside is that we have to do this optimization for each instance, for each scene that we captured. On the other side, we also have learning-based solutions starting to shining out recently, and it's generalized well to the new captures, new data, new instance. But the downside is, of course, we need to train a model, which is super expensive, at least nowadays. So during my PhD, during my 4 years here at Berkeley, most of my efforts have been put on the first paradigm to improve the efficiency of the optimization-based solution. And approaching to the end of my PhD, I also started to look into this learning-based solutions, and there is ongoing work called Probe, which I will briefly touch upon in this talk as well. So this is the agenda of the talk today. First, I will talk about the ways to improve efficiency in nerve-based solution, including 3 different axes: representation, volume rendering, and multi-GPU, which is the resource, how to efficiently leverage them. And secondly, I'll talk about the efficiency in 3D Gaussians a little bit through this library called the G-Splat that we developed here. And lastly, I'll briefly touch upon how to improve efficiency in learning-based approach to make it less expensive to train. Okay, I'll start with the NERF. I think most of the people here know about NERF. It starts from a casting array from the image into the 3D, and evaluate and discretize the array into multiple samples, then evaluate each sample with a neural network. After the evaluation, we get the color and density. We could accumulate them back to the image plane and perform supervision on the image plane with the loss per pixel loss. So if we look into this pipeline, we could figure out where the runtime, which part actually contributes to the slowness of the initial nerve. First of all, is this network evaluation. We need to evaluate every single point through this network. Of course, the slower it is, the more slow it is, the more slow the entire pipeline is. And also, we need to discretize the array into samples and evaluate all the samples. That means our runtime is also proportional to the number of samples. And the last part is probably not that obvious, but since we run everything on GPU, the more resource we have, we should expect it to run faster than just using a naive single GPU. So now we have different these 3 aspects: representation, sampling, and resource. And I will go into each one of them and provide some solutions for it. So the first is about this project called Octrace. It's actually the first project that I got involved when I joined Berkeley. And the idea here is that, okay, NERF was slow in both training and the rendering. And what if we could make it like render in real time after the training? That would be already pretty awesome. So the high-level overview of this is that NERF initially was just an MLP network, which is slow to evaluate. But what if we could turn this MLP network into a voxel-based representation? And the benefit of that is evaluating the voxel is way faster than evaluating the MLP itself. So the key idea here is to factorize the NERF representation, which was a 5D plan optic function taken x, y, z, and real direction, into a formulation that only takes in the x, y, z location, so that we could cache it with a 3D voxel grid. And the spherical harmonics is the key to allows us to factor out the real direction from the input. So with the spherical harmonics coefficients, we now can represent the NERF as a sparse voxel grid, with each voxel stores the spherical harmonics coefficients as well as the density. And this allows us to query this representation in a super efficient way. So what it achieves is like 3,000 faster than rendering NERF, like a very crazy, like real-time rendering speed, and without compromise the quality. So after that, there has been a lot of work focusing on improving the representation of the nerve, either trying to make it more efficient or making it more generalizable to not only static environment, but also dynamic environment. But as we can see in our formula before, a network is only part of the story. There is also another factor, which is the number of samples along the ray, which contributes significantly to the runtime. So this brings us to the next project called NerfVec. And the goal here is that we look into this sampling perspective, sampling aspect in the nerve formulation, which is a shared formulation across all type of representations. And by doing it in a smart way, we could accelerate all type of nerves, including the nerves doing static scene reconstruction, and also nerves doing dynamic scene reconstruction, and even the nerves for doing camera optimization. And in this project, we built a toolbox called NerfVec, which you could just pip install it on both Linux and Windows. And we designed it with user-friendly API so that with less than 100 lines of code change, you could plug it into your code base and enjoy the speed up. So the idea here in this library is that we want to perform this sampling in an efficient way. But let's say if we don't know anything about the volume, we don't have a structure prior. The best we can do is just a uniform sample along the ray. But this is not ideal because 3D is sparse. It will produce a lot of wasteful samples on those empty space. And during the nerve optimization, since it converges to something really sharp, we should be able to figure out the place to skip during the training. So one way of doing that is to online distillate a nerve into an occupancy grid where we can skip the empty space guided by this occupancy grid. And there are some papers doing spatial skipping in this way. And of course, each one has its own customized implementation. And in this project, we kind of unified all the formulation in the toolbox. And also there is another way that we could first create a uniform sampling. And this uniform sampling allows us to compute the PDF along the ray, which could be used to guide the second round of sampling that create denser sample around the surface. Original nerve used this strategy, and including some other follow-ups like MIP nerve 360, and also zip nerve later on. So these two different approaches seemingly very different from the way it behaves. But we figure out from the perspective of important sampling, they all can all be formulated in a unified formulation, which is to estimate the transmittance along the ray. And since we unified them with this like transmittance estimator to describe each formulation, we could put them in a same framework and implement them in a fair ground. So that allows us to do some systematic comparison between the two, and we realize they perform differently on different type of data. And also allows us to easily combine these two approaches together to enjoy the best of both worlds. And here are just the results that if we use our library in those existing code base, we could enjoy like a significant speed up. And not only the speed up, we also see most of the time the quality got improved for both dynamic, static, and even camera optimization. And we feel that it might be this sparsity prior that we are using kind of reduce some floaters in the nerve reconstruction, which helps with the quality as well. So some visuals. This is plugging it into the tensor, got 3 times speed up and better quality, and plug it into the K-plines, which is a formulation for dynamic nerves, and also plug it into the taniovoxel. It's another dynamic representation of nerve that works on the real data captured in the wild. So it's also being used by many open source libraries like Nerve Studio, SDF Studio for mesh reconstruction, 3 Studio for 3D generation. Even this application from Luma that does this text to 3D also use NerfX to speed up the rendering. So now we have discussed the representation. We have discussed how to improve the efficiency in the volume rendering. There is another factor, which is that if we have more resource, how could we leverage those resources in an efficient way to further boost the efficiency of the system? So I've been interning in NVIDIA for since 2022 and working on this project called NerfXL, trying to scaling up nerve optimization solution with multiple GPUs. So Nerf was great on small scenes because it needs to allocate some parameters for the spatial content to memorize those details in the area. But when we scale it up to a larger environment, the parameters that we need to memorize those details keep increase. And at some point, it will exceed the amount of memory that could be hosted by a single GPU. And in this project, we explored Nerf on a much larger solution, up to this 25 kilometers square, the whole city area, and reconstructed with multiple GPUs. So the goal here is to find a solution that, when leveraging multiple GPUs, they are equivalent with using a much larger GPU that does not physically exist. We don't want to compromise on any hyperparameters. We just want to find it from the mathematical perspective, equivalent solution. So naive solution actually that supports multiple GPU is like this. Okay, I think the color is a bit off and there are some lines not showing here. But the idea is that we could chunk the space into multiple subregions and let each GPU handle each subregion so that the amount of parameters living in each GPU is feasible to do the reconstruction. And a simple way to achieve the joint training paradigm across all GPUs is that we could distribute the samples along the array to different GPUs based on which tile it belongs to, and produce the color and density, the network evaluation in each GPU, and then accumulate them in a single GPU for the final volume rendering. But this is not ideal because from the paradigm, you could tell there is imbalanced workload when GPU 0 is doing the job of volume rendering and loss computation. GPU 1 and 2 are just idling. And plus, we need to transfer data in both a forward and backward paths from other GPUs to GPU 0, which is also not ideal for the more than multi-GPU system, because data transferring can always be a bottleneck most of the time. So we look into the computational graph of the system, and we realized that there is a trick that we could apply to separate this computational graph into multiple branches. And what that means is that in practice, we could repeat this volume rendering process in every GPU, meaning that every GPU does this rendering independently, but all of them using the same data that broadcasted from all the GPUs. Okay, so the lines are not clear here, but basically every GPU broadcast is samples to all other GPUs. So every GPU doing the same volume rendering process and compute the loss and doing the back propagation. And this means that we don't need the back propagation to go through the communication across GPUs anymore. So only the forward pass, we need to distribute the samples, and then the backward pass can be done purely locally, allows us to remove this half of the communication needs to happen. But this is still not ideal because we distribute all the samples, which could be easily to be like a median level of median for each rendering. So we want to avoid distribute the samples directly to GPU as well. And the way we do that is to revisit the volume rendering integral formulation. We realized that it could be rewritten into a hierarchical of a volume rendering integral. What it means that we could perform volume rendering locally within its GPU and accumulate all those samples into a single color value and only distribute this color value to different GPUs. So this allows to reduce the amount of data we need to transfer from number of samples to number of reads, which is usually like 10 times or more smaller amount of data need to deal with. So this system is kind of a general system that scales up NERV to multi-GPUs without any assumptions on what the data look like. So we test it out on all kinds of data. And it works well. Here, the red lines are our approach, and the blue and green are the previous works. So we could see that using more GPUs, we could keep getting better performance, and we could also keep getting faster rendering speed at the same time. Because we have more memories to host more parameters, we have more threads to have better parallelization. And the visuals, from the visuals, we can also clearly tell it's keep getting better with the quality when more resources are being used. So here is another visual that we apply this NERV to this entire Mexico beach city, covers 6 kilometer area. The data was captured using drone, fly over the city, and we take the image, register it, and reconstruct the entire city using, in this case, I think 32 GPUs. And we could keep all those details. And another example that we go even crazier to a 25 kilometer square area, which is the entire city being modeled by a single NERV, lived in 64 GPUs, I think, in this case. Okay, so up to now, we have talked about the efficiency in NERVs from 3 different perspectives: the representation, the sampling, and the resource. But as we mentioned, there is another kind of way to doing optimization approach came later, which is the Gaussian splatting. And Gaussian splatting is a little bit different with NERV in a sense it is not accumulating this per pixel value from samples along the array. It's directly rasterizing all the Gaussians in the 3D space into the image plane. So now with this new formula, the runtime analysis actually changes. We don't have network evaluation in Gaussian splatting because everything is explicit. We don't have sampling procedure because there is only the rasterization process. But we still have the issue of how to use multi-GPU for Gaussian splatting, but I will touch on later. So now what really matters for Gaussian is this like rasterization process, like how to make that efficient is the key to accelerate the Gaussian splatting optimization. And so this actually brings us to the next project, which we realize, okay, implementation really matters. Like we could fuse every calculation into a CUDA kernel, and through well-executed programming, we could actually get much better efficiency for Gaussian rasterization. And this is gsplat. It's a collaboration with Wiki and the entire NERV Studio team. We put a lot of efforts on developing this library. And we realize up to 4 times less memory footprint than the official implementation, and up to 15% of faster training on a standard benchmark. But standard benchmark actually doesn't tell the full story. We also tested out on hundreds of millions of Gaussians, and GSplat could render it smoothly, while the official implementation suffers with the speed, so it only gives the low resolution results. And we also support this multi-GPU distributed training and rendering similar for NERV that the project that we introduced before. But this time we are using existing approach like published recently, and works pretty well in the large scale data, the same data that we demonstrated before. The entire Mexico City is being reconstructed here using Gaussians and visualized here in real time. And also we support the many different type of cameras in GSplat. Those are also part of the extra features that we provided for users, including fisheye, compression, and support random initialization to get rid of the reliance on CoMap. And also meshing algorithm in GSplat. So, and some other features. So yeah, this is kind of a screenshot of the GSplat API that have all those arguments. Probably each of them is a feature that we included, and is keep growing right now. And so yeah, GSplat has been growing a lot since its first release in 2023, and I think we have plenty of audience right now. And we also collect a lot of feedbacks and help us to improve the GSplat a lot from the community. Okay, so summarize. Oh, actually not yet for a summarize. This is just a summarize for the optimization-based approach that we introduced before. We have NERV and Gaussians. But we still have another paradigm we haven't touched upon, the learning-based solutions. And this is the part that we will touch upon a little bit next. So here is the same size as before. We have a lot of learning-based approach developed recently. But they all are kind of using this multi-view transformer to do the job of 3D perception from multi-view inputs. And that means we have images, cameras from different perspectives, and we want to fit them into the transformer so the transformer could understand the relationship between those cameras and the images and perform the downstream tasks, like, for example, non-view synthesis, depth estimation, and even more complicated tasks. So the key here is to have the transformer to learn the ability to learn the relationship between the input images from different viewpoints. So how to do that? There is a dominant strategy recently, used in all of previous works that we mentioned, is that we inject the camera information as a per pixel remap, which mark the origin and the direction of each ray that goes through the pixel. And we could concat this remap with the pixels and forms a very simple kind of higher dimension input for the transformer to learn. This generally works as demonstrated in the previous works, but this looks weird because it encodes the absolute coordinate system into the system when you convert the camera into the remaps. And this doesn't feel ideal because we as humans don't really have an absolute coordinate system. We always understand things in the relative world space. So ideally, it should be like same for a model that understand the relationship between cameras in a relative way instead of in a fixed coordinate system. So this brings us this project called projective positional embedding. It is motivated by the rotary position embedding, which encodes the relative position distance in large language models. We want to do the similar thing for cameras as well. We want to encode the camera information into the transformer in an explicit way that respects the pairwise relationship. So the solution is extremely simple. We just treat each camera, we just formulate each camera using a perspective transformation matrix, which is a 4x4 matrix. And we could inject that matrix into the tension calculation, which brings little overhead to the tension and explicitly inject the relative transformation information into the tension. So with this simple change, we could get the model to converge much faster. The blue lines are using the Parker as input, and the black line is using this probe formulation here. And we could get much better convergence in the end as well in this task of novel synthesis. And we also tested on different tasks, like zero taps estimation. We got similar results that reduce the error a lot. And we also tried it on interesting kind of spatial cognition task where we ask a question of which image has the wrong pose among all the inputs and formulate it as a classification problem for the transformer to figure out. And it does pretty well with this probe formulation because it explicitly injected the relative camera information, positional information into the tension, while Parker is still doing okay, but much worse. Okay, so that comes to the conclusion, actually. We have introduced different ways to improve the efficiency in nerves through better representations, through smarter sampling, through using more resource efficiently. And we also introduced the solution for 3D Gaussian, basically have carefully fused CUDA kernels for the rasterization implementation. And lastly, we also introduced a way to inject the 3D information into the tension so that it could respect the 3D relative position of the cameras that leads to faster convergence and a better understanding of the data. So the takeaway that I want to share in this presentation is that efficiency in 3D perception is kind of special because we have a lot of 3D prior knowledge. And the question that I've been always thinking is that how to use those 3D prior knowledge that is special for the 3D field to keep improving the task that we are doing in 3D. For example, we have used a couple of prior knowledge in this talk. 3D is sparse, and we have the volume rendering formula to build a bridge between 2D and 3D. And we also know that in 3D, the camera relationship could be represented as a relative projective matrix. Something like that could keep going on, but I think that's a pretty interesting way to think about 3D, where it distinguishes the task in 3D with all those general machine learning tasks. Okay, going forward, I guess I would just always wondering what are the 3D prior knowledge that we could leverage for building the next generation 3D perception model, like the attention in the transformers. What is the best way to do the 3D perception model in a unified way? Okay, so here is a list of papers that didn't fit in this slides. So I'll just list them there in case you're interested. Okay, so it comes to about to come to an end for the presentation. And of course, I am really grateful for all the advisements and mentoring during my PhD. I really want to say this big thank you to Andrew. I probably haven't tell Andrew this, which is you're the only reason that I chose to join Berkeley to begin with. And because the time spent with you is So it's so pleasure, and I don't want it to finish. And your attitudes towards life and research are very inspiring, like always enthusiastic. I think that's the part I really need to learn from. And I do learn a lot from you, like during the past 4 years. And also Hao is my previous advisor at USC for my short 2 years PhD journey there. He's also a really good friend to me and give me a lot of advising in the both research and life. He's now a professor at Abu Dhabi, and I hope to see him again in the future. And yeah, so Sanya is the advisor that I met and at NVIDIA when I was intern there, co-hosted by Francis and Sanya. And Sanya was pretty kind. He introduced me to a lot of folks in NVIDIA and give me a lot of pleasures, give me a lot of exposures through the resource of NVIDIA. So I'm really grateful for her on giving me all the supports and helps. Shan is a great mentor. She is the first industry mentor that I have ever met when I started my journey at United States. So I interned with Shan at Google, and where Andrew was also my host there. And I still remember the time that I was pair programming with Shan on this project of AI dance generator. And all my coding skills actually come from Shan. Yeah, I learned a lot from Shan, and I think without her, I wouldn't be able to do all those amazing projects afterwards. So Francis is also a close friend, also a mentor of me at NVIDIA. He is also a great engineer. And I kind of further developed my CUDA skills, learned from Francis at NVIDIA. So I'm really grateful and for meeting him at NVIDIA as well. And Christopher is a person that I met at Meta when I interned there. He was also very kind and always helpful. And I'm glad that he is now around the Bay Area, and I got to meet him a couple of times during the past year. Yeah, I just want to say thank you for all the advisors and mentors that I met during my PhD. And also, I can't finish any of those projects without my amazing collaborators and lab mates, including Hang, Alex, Junchen, Brent, Vicky, Ethan, Chenfeng, Jeffrey, Ming, David, Michael, Zeng, Yuliang, Shensky, Junlang, and Kyle, and all the amazing lab mates. Yeah, I've been having a really great time here, all because of those amazing lab mates and friends. So also, I definitely want to say thanks to my mom and dad. And I'm putting a star there to demonstrate equal contribution here. So also my wife here, I think in China, she's in China right now, along with my mom and dad. It's pretty tough actually to be here along doing PhDs during the past 4 years. But I'm really glad that I have all the supports from my family, including my wife coming to visit me a couple of times, even during COVID. So yeah. And of course, my two cuties that I have met like 2 years ago had always been running around in my house and encouraged me to like do more works and chill up. Yeah. So also roommates here are probably the closest friends of me, except for families. And we have been spending a lot of happy time together. And I'm really happy to have their supports along the way. And here just another set of friends from new to old. Yuxi is my my friends in high school, and Dongyang here is my friend in middle school. We keep a really good relationship from very little. Also, I have met a lot of amazing friends here in conference at different places. So yeah, I'm really happy to have this PhD journey here, and hope to keep all the relationship with all those amazing peoples and keep going. Yeah, that will be all for my talk. Thank you, everybody.
Very nice. Okay, questions or comments?
Hey, Ruilong, awesome talk. Yeah. So the last project, the probe was kind of more towards like generation. Do you kind of have like do you know what you want to work on next? Like, do you want to work on reconstruction and generation or just go the generation route?
Yeah.
How are you feeling about this?
Yeah. That's a great question. I feel like generation and reconstruction nowadays, there isn't a clear bond between them. Like reconstruction is basically a generation under well condition. Like you have many signals already, and you just recover it. And in real life, probably there isn't a pure reconstruction anyway, because the captures from real life always like have some missing parts, have some missing perspective angles, view angles. So I think they are always like part of the same system, like the generation and the reconstruction. So yeah, that's a great question. I feel maybe so in the PhD journey, most of the time was purely doing reconstruction, and now I'm kind of feeling okay. I should treat them as the same problem going forward.
Are you interested in like 4D insights as well? Like you have so many like 3D tricks about how to like compress and speed up.
Yeah. So for the 4D is hard. I did a project when I was in Meta on human reconstruction that was kind of 4D, having the time access. But I stopped doing that because after that project, I feel this is so hard problem. But yeah, I think nowadays with all those foundation models to help with, to give us better priors, I think it's become more realistic to do it. To solve it, and maybe I'll bring it to the table again someday. Yeah.
Cool. Thank you.
Thank you.
Okay, on that note, I think technically you've been working on lots of representations, right? Explicit, multiple versions of it, and implicit. And what do you think is like the path moving forward? Because, for example, there's a NERF and GS kind of evolution. Mm-hmm. But do you think there's going to be another one, or are you all in for the implicit thoughts?
Yeah. That's also a great question. So implicit has its benefits because we don't need to go through all those like explicit volume rendering, rasterization, crazy implementations. And but explicit also has its benefits of some guarantees on there is underlying structure there. Going forward, I feel that these two routes should merge, and we should have a system that injected the optimization or the explicit in it, but also having the ability to be flexible about the representation as well.
Yeah, arguably it's already mixed because even if it's implicit, you will read it out into an explicit representation, right? So then in that sense, do you think there's going to be I like another versions of GS? Like what's the missing aspects do you think that really matters? Do you think it's necessary or do you think it's all good?
No, I think Gaussians are pretty easy to deal with because it's all just explicit Gaussians. That's a benefit, but it doesn't. It still doesn't give you all those like graphics guarantees, like the reflectance and everything. Only moving a small step forward on top of NERF, I would say. But keep going forward, I would say it will go into this very graphics kind of domain. You will have all those retracing kind of coming in, which could be crazy. I think for the from the realist aspect, we just want to have a balance between how accurate we want to get from the graphic side, and how flexible we want to get from the machine learning side. And different applications might want different amount of like the adjustment between the two. So yeah, I think probably that's a problem based on the real application. Like the answer probably depends.
Any other questions? Okay, then last question. What was your biggest lessons from your PhD? What do you, yeah.
Yeah. Yeah, I feel having supports from others is really important. Like being in an environment that you have friends, you have lab mates, and you have people to talk with. Um, like um, like both emotionally and also like professionally, like all those ideas come from the discussion with friends and the collaboration with friends. Yeah.
Okay, all right. Well, let's thank Ruilong again. And thank
Thank you. Yeah.